Okay, guys, sorry for the delay getting to you. I've had a whole host of technical problems, which I think I've overcome now. This is my, I'd say, 10th attempt to make this video, so I can see the evidence of the past one here. So, first off, this is the first of the homework questions I gave you, and we're going to go through the ordinary level question and then the higher level one. Now, in the meantime, if you've lost or handed in the actual question and you don't have a hard copy in front of you, I'd suggest taking a photo of this screen now while it displays the question using your phone, and then you can refer back to it as I go through the question. So there's the ordinary level one, and the higher level one is crickety job. So I'll do that in maybe two sections. There's the first part. If you take a snapshot of that, you're using your phone, and there's the second. Now, if you have the actual physical copy beside you, that's even better. Okay, so let's look at the ordinary level question first. SpaceX rocket carries two astronauts launched from the Kennedy Space Station. Just zoom out a little bit there, give you a little bit more room to play with. So 15 minutes after launch, it appears in the sky over Ireland. So 15 minutes have passed, and it has travelled at that point 6,484 kilometres. Calculate the average speed. Well, first off, always just write the formula you're going to use. Even if it's a really simple one like average speed is equal to distance travelled over the time taken. Now, straight away, you might be tempted to just put in the values. So if you put in 6,484 kilometres and divide it by the time in minutes, which was 15 minutes, well, you might be tempted to do that. You would get a valid answer, but the units wouldn't work. Kilometres per minute are grand, but really we're looking at meters per second in physics. So it's a bit of a trap. First thing I want to do is convert that. 6,484 kilometres is 6,484,000 meters. That's the distance travelled in actual meters. And in time, 15 minutes times 60 seconds. That will give us our answer in the System International Units, which we're looking for. So let's try that. 6484000 divided by 15 divided by 60. So I get an answer of 7,204.4. Oh, nice. How's it going? Meters per second. So that's in the proper units, that's what we're looking for, ground stuff. Now, if you kind of fell for the trap, if you just divided your 6,484 by 15, you would end up with 432.2 recurring, and that would be kilometers per minute, which, while it's a valid answer, we really want it in meters per second. So in either case, make sure you give your units, and that's the one we're really looking for. Okay, second part. The rocket later docked at the ISS. The ISS orbits the Earth every 93 minutes. How many times does it orbit each day? Okay, first off, let's find out how many minutes in a day. Well, there's 24 hours, and there's 60 minutes in each hour, so 24 times 60 is 1,440 minutes in a day. So how many times can this ISS go around the Earth in that time? Well, if it takes 93 minutes each time, how many 93s are there in 1440? So just divide by 93 gives me an answer of 15.48 blah blah blah. And that's how many full revolutions it makes. Now we're looking for full revolutions, so we don't care about the decimal, because the question asked full orbits, 15 full orbits. That's the second part. Okay, Newton's law of universal gravitation describes the force of attraction between the ISS and Earth. State the law of universal gravitation. Well, I'm going to kind of describe this verbally, and you can write it down in words, that the force of gravity is proportional to the product of the masses of the two things involved, of the two bodies, divided by the square of the distance between them. Now, if you just wrote that as exactly as it looks in front of you, you wouldn't get full marks, because you need to say what each one is. So F would be the force of gravity, M1 is the mass of the first object in kilos, M2 is the mass of the second, and D is the distance between them squared. You might have gone to your logbook and written the full equation, which is going from proportional to making it the full equals using the gravitational constant. Gravitational constant M1, M2 divided by D squared. Both valid, but you have to say what each one means, what each letter means. Okay, on to the second part of the question. And a couple of little trick questions here as well. I'll just go over this section here. Fresh. So the ISS is located above the Earth's surface, 400 kilometers above it. Blah, 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 blah. Okay, calculate the astronaut's weight on Earth. Well, if they have a mass, well, first off, write out the equation. Weight is equal to mass times the acceleration due to gravity. So that's equal to 805 kgs times 9.8 meters per second squared. So he has a weight, or she has a weight of 9.8 times, so that's 833 newtons. Make sure again, give your answer in newtons because you're looking for weight. Now, a little bit of a sneaky question, part 5 even. What is the astronaut's mass at the altitude of the ISS? Well, whatever that astronaut's mass is, in this case 85 kgs, that's their mass all over the universe. It doesn't matter where you go, your mass will be 85 kgs. So that's the answer. It doesn't matter where you are, your mass is 85 kilos. Your weight, on the other hand, for part 6, is different. So calculate the astronaut's weight at the altitude of the ISS. Well, we know their weight was 833 newtons on the surface of the Earth. And we know that when you go up to the ISS, you're only getting 90% of the gravitational pull. So all I've got to do is multiply 833 and get 90% of that. Easiest way to do that really is just multiply by 0.9. That'll give us our 90%. 0.9 gives me an answer of 749.7 newtons. Now, that's the ordinary level question. We're going to go on to the higher level one in just a moment. I'm going to pause it there and get a fresh piece of paper. Okay guys, so looking at the higher level question, state Newton's laws of motion. So you have to be pretty precise here and actually spell them out for the examiner. Newton's first law states that every body will remain in a state of rest, or if it's moving, it will keep at a constant speed unless an external force acts on it. The second law of motion, that is when a force acts in a body, it will accelerate in the direction of the force and its rate of change of momentum will be proportional to the force. One more time. So when an unbalanced force acts in a body, the rate of change of the momentum is directly proportional to the force and goes in the direction of the force. And finally, and you can't really get away with just saying equal and opposite here, as a couple of people have tried, you've got to be detailed, like write out the words. States if a body A exerts a force on body B, then body B exerts an equal but opposite force on body A. So action and reaction equal and opposite, but you have to be detailed. Okay, show that F equals ma is a special case of Newton's second law. All right, well, let's start off with Newton's second law. So the force is proportional to the change in momentum. So the change in momentum is mv minus mu over t. So the force is proportional to the change in momentum, mass times the final velocity minus the mass times the initial, over time. Okay, well, looking at the top line, I can take m out of both of these because it's a common factor. So F is proportional to m into v minus u all over t. And v minus u over t, there's another word for that, that's acceleration. Because a is v minus u over t, I can just sub in a instead of all this. So we've got the force is proportional to the mass times acceleration. Now, to get this to be equals, that we need this constant of proportionality, we need this weird k. So basically what this is saying is that if you increase the force, you get an increase in mass times acceleration as well, but we don't know what the relationship is. If you double the force, how much does this go up by? And that letter which we don't know, the number we don't know, we use k for that. So kma. But luckily for us and the way the units are set up, and this is where loads of people lose lost marks, you're grand so far, but you've got to specify that because 1 Newton gives a 1 kilogram mass an acceleration of 1 meters per second squared, therefore k is 1. So we can go from F, that should be an equal sign there, sorry guys, F is equal to kma. That means F is equal to just ma, and that's the second special case of Newton's second law proven. You might want to make sure you're solid in this. Read through the example in the book. It's in the chapter on force, mass, and momentum. It's around page somewhere between 90 and 100. Make sure you're solid on that, especially that last bit about the units and getting rid of the constant of proportionality, because that question comes up quite a lot. They're fond of that one. Okay, describe an experiment to find the resultant of two coplanar vectors. A lot of people wrote really detailed answers but of the wrong experiment. So this is one where you're trying to find the resultant of two vectors when all three of them are acting on the same plane. So what you do is you tie a knot in a piece of string, with 3 kind of pieces of string coming off it. You hook up Newton meters to each one, and you adjust the Newton meters until, so you can pulling on each one, so there's a hook there, a hook there, a hook there. You pull on each one until the knot is no longer moving. Now the reason for that is when the knot is no longer moving, it's at rest. The forces are balanced, there's no acceleration on anything. When that's the case, all of these 3 forces, which are the tension in the string, are equal. Now, in terms of finding the resultant, we've got these 3 set up. Any one of these forces is the resultant of the other 2, but in the opposite direction. By which I mean, these two pieces of string are trying to pull the knot. Let's just switch this card if you want. Trying to pull the knot in that direction. And if it wasn't for this force pulling it directly against that, They would. The knot would accelerate in that direction. But this force here is acting in the opposite direction of the resultant of these. So the resultant of these two forces here is in this direction with a magnitude equal but opposite to the third fella. Now that's a lot of explanation and it's a lot to take in. It's also tucked away, that little experiment is tucked away somewhere in the chapter. I can't remember the page number, I'll post it after the fact. Read through it, make sure you're solid on it, because again, that one can come up quite a lot and it's deceptively tricky. Okay, where are we at? So that is 29 marks so far. Okay, let's keep moving. So now, solid example. A cricket player moves her hands away from the motion of the ball as she catches it. Use Newton's laws of motion to explain why she moves her hand away from the motion of the ball. Okay, well, let's go back to Newton's second law. The force is proportional to mv minus mu all over t. So you have to kind of specify why doing this helps. When the cricket player moves her hand away from the ball, what she's actually doing is prolonging the time of impact. So because t is increasing, because she's making t longer she's not making brewing tea, because she's making the impact last longer, the overall force is going to be smaller because you're dividing by a bigger number. So because t increases, the force is going to decrease. By the way, this is just me talking. You should be writing these out in words when you're doing your answer, okay? If I gave that in as an answer, the guy would have no idea what I'm talking about. So as time is increased, the force will decrease. You have to make sure you've specified that as well. Okay, it's only a little handy. Those are 3 marks, 1 for that. Now on to the meat of the question, where things got a little bit tricky. Okay, folks, I had to pause the video there because Doofus here left his calculator in radians and would have gotten the wrong answer altogether from when we were introducing circular motion. So I just switched that back to degrees. Okay, so we're on to the kind of the tougher part of the question, where the cricketer throws a ball at 45 degrees to the horizontal. So I'm just going to sketch it out. So she throws the ball at 45 degrees to the horizontal with a velocity of 28 meters per second. Now this 1.6 thing, that's where she starts. So I can imagine that she's got a weird arm, wherever this meant to be her arm. So it starts off there at a distance of 1.6. That's going to become significant later in the question. But for now, let's focus on the angle. You can't see what I'm doing because I'm off screen. Sorry about this, guys. It's been a while and rusty. All right, so we've got a velocity of 28 meters per second. 45 degrees to horizontal. Now I need to break that down into 2 components. How much of that throw is horizontal, which I'm going to call hor, and how much is vertical, which I'm going to call vert. Okay, so how much of this 28 meters per second is used to just go straight up, and how much is used in the horizontal direction? So to do that, I'm going to need a little bit of trigonometry. So I'm going to treat this as a right angle triangle with a hypotenuse of 28. In this case, our unit is meters per second, and an angle here of 45. Now this will work for any vector, guys, and it's the trigonometry that often throws people, so be more comfortable with it. Practice, practice, practice. Speaking of which, what are the ratios? I remember as silly old Harry, so sine opposite hypotenuse, chased a horse through our attic. That's how I remember it. Some people just go Sokotoa, whatever floats your boat. Okay, so sine is opposite of hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Now, what do we need here? Let's get the vertical component first. So the vertical component is equal to, now which of these ratios is going to work? We know the angle is 45, we know the hypotenuse, and from this angle, the vertical component is opposite it. So we're looking for the one with the opposite and hypotenuse, which is this guy. So the vertical component, let's go with sine is equal to opposite over hypotenuse. And we know that the angle is 45, so sine 45 is equal to the opposite, which I'm going to say vertical, because that's what we're looking to figure out, the vertical component of the vector, divided by the hypotenuse of 28 meters per second. So I'm going to bring that across. 28 meters per second times sine 45 will give me the vertical component. So now that I've changed my calculator back to sines, or to degrees, let's go with sine 45 times 28. I'm going to have to press SD to get a decimal version of the answer, and I'm going to go to 19.79, let's go 9 meters per second. Now that's my actual value, but I'm just rounding up 3 decimals to do the job. So that's the vertical component. Now because we're dealing with a 45 degree triangle, the horizontal component is also going to work out that, but let's just check it anyway. Let's just get in the habit of doing both. So the vertical component is that. Now later in the question we might need the horizontal one, so let's have a look at that. This time we know the angle is 45, The hypotenuse is 28, but we're looking for the adjacent down here. So we're going to use cosine. Cosine of 45 degrees is equal to the horizontal component divided by the hypotenuse of 28 meters per second. So I bring that across. 28 meters per second times cosine 45 will give me the horizontal component. So again, calculator. Cosine 45 times 28. Again, 19.799. Now, the reason I kind of done that, you might think, why bother doing that when it's 45, it's kind of the same? It's because it won't always be the same. So be in the habit of being able to calculate the vertical and the horizontal. So now we know the two components that we're going to be dealing with. Let's go back to the question. What are they actually asking us? So she throws the ball, and we need to figure out how long the ball was in the air, the horizontal distance it travelled, and the maximum height above the ground. Or let's deal with how long the ball was in the air first. Because here, it's suvat time. So we're going to look in the vertical direction. What do we know? We know that the initial velocity, the vertical component of the initial velocity, was 19.799 meters per second. We know, now here's the tricky thing, when you throw a ball, it goes up and then it comes down. Now in terms of vertical movement, during this section, it's going up, but it's going up less and less fast. It's decelerating. When it's falling down, it's going down, and it's getting faster, faster, faster. But what we're looking for is this point here, just the exact point where it stops going up and hasn't yet gone down again. And at that point, it's just, if you imagine going, whoop, at that moment, if you freeze time, it isn't going down, it isn't going up, so its velocity in the vertical direction is 0 meters per second. Now we know that acceleration is going to pull things down with an acceleration of 9.8 meters per second, and that's negative because it's going down. So we've got most of what we need. We just need the fourth. Now, I keep harping on about your logbooks and about how you don't have to remember the suvat equations because they're all there, page 50. So let's see which one is going to be useful to us here. We know V, we know U, we know A. We're looking for T, we're looking for time, how long the ball was in the air. So I think easiest one here is this guy here, V equals U plus AT. See if that helps us. V equals U plus AT. Because we know V, we know U, we know A, we just don't know T. So let's rearrange this. V, bring the U across, minus U is equal to AT. And let's get what we need on one side, which is the T. So V minus U divided by A will give us our time, how long the ball was in the air. So V minus U is 0 minus 19.799 meters per second divided by the minus 9.8 meters per second squared. So I'm going to go more precise and use our answer that was already there. Divided by 9.8 gives me a time of 2.02 seconds. Now to be careful here, because what we just calculated is the time it took the ball from when she released it to the peak of the throw, which was 2.02 seconds. But it's actually going to take another 2.02 seconds to fall down again on the other side. So the total, even though for our answer there is 2.02, the total flight time is 4.04 seconds. That's how long the ball was in the air. Okay, so that's the first part. How long the ball was in the air? 4.04 seconds. The horizontal distance traveled by the ball. The good news is this is going to be a lot easier. We know that the horizontal velocity is 19.799 meters per second. Okay, so we know its velocity when we know the time. So this time, let's just go much more simple and let's go with speed is equal to distance over time, or velocity is equal to displacement over time. Doesn't matter too much for this one. Now we're looking for the distance, so bring the time across. So the time it was moving, times the speed it was moving at for that duration, will give us our distance. So the 19.9799 times 4.04 gives me a distance of 79.98 meters horizontally. That makes sense again. If we got a 700 meter throw, things might be a bit wobbly. Or if she only threw it like half a meter or something, things get wobbly. That makes sense for a cricket throw, 79 meters. Okay, finally, the maximum height above the ground reached by the ball. So what do we know in terms of vertical stuff? Well, we know, going back to our earlier equation, we know that if the duration to get up to there was 2.02, so let's get the displacement from here. So again, which of these is going to do the job? Let's keep our life simple. Let's go with s equals ut plus half at squared. That should do the trick. S is equal to ut plus half at squared. I think you could use one of the others as well, but I'm just going to use this. So that displacement is equal to ut, so it's 19.799 meters per second, times the duration of this time. We're going to use how long it was going up, times 2.02 seconds, plus half, multiplied by, I've probably chosen the most complicated one actually now that I think about it, minus 5, times the time squared, which is 2.02 seconds squared. Yeah, I probably have. Well, we'll persevere. So let's go with 19.799 times 2.02 plus, I'm going to use some brackets here, 0.5 times minus 9.8 times 2.02 times 2.02. What did I get? 20 meters. Yeah, that makes sense. 20 meters is the total height. Now, the last bit of the trick question. The ball went 20 meters from the starting point. The sneaky thing here, though, is they were already 1.6 meters above the ground, so the total height they reached was the 20 meters plus the 1.6 of the starting. So for that one, it's 21.6. All right, that was tough. The last part. Draw a diagram to show the velocity and acceleration of the ball when it's at its maximum height. So it's on the peak of the throw. So let's say that's the ball. Okay, at the moment, its acceleration is going to be downward because it's being pulled by gravity. So A is down. What else do we need to see? Velocity and acceleration. So acceleration's done. The velocity, let me get this straight in my head. I think it's just moving in that direction. It's moving horizontally. It's no longer moving up or down. So that's V. And the force is on the ball. It's just gravity, so that F is pulling down as well. Boom. Well, there's the force moving it down, and then you don't need to worry about a horizontal force because it's moving at a steady speed because we were told we can neglect friction. Right, guys, bit of